This UCSD TV program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest programs.
I will start since as a convener of this next session, and I will ask Mischa to come later. You know, I think it's what Lou asked. It was absolutely legitimate question, and I think if society, not only bureaucracy, but society, would not be told what happened, why it was originally planned for 5 billion ITER. Now we're talking about 55 at least. So what happened? Something, you know, has to be clarified. So before we are going to space and astrophysics, I would like to say a few words. I'm probably the only survivor of earlier period, not 1961. I joined fusion program in Soviet Union at Kurchatov Institute since 1956. And then there was a famous Geneva conference in 1958 with all this, you know, the great people, you know, like Lyman Spitzer, Marshall Rosenbluth from America coming. So I was there, and it was almost officially declared at Geneva in 1958 that fusion energy would be harnessed in 20 years. It was coming from the mouth of chairman of Geneva Conference, prominent Nobel Prize winner, Indian physicist Homi Bhabha, and Igor Tam, co-inventor of tokamak, was a co-chairman. He was sitting next to him. But you know what happened? Nobody actually noticed the rules of the game for fusion changed dramatically since that time. How initial role of fusion was very simple. So in a couple of hundred years, assumption was that we will get rid of conventional fuels, so they will move to nuclear and fission energy. And we know that how much we can extract uranium-235 out of natural uranium ores. It would probably sufficient for few hundred years, maybe a couple of thousand years. And then people said, then we will use fusion. And this is how actually, Charlie, first connection between plasma physics and fusion and oceanography came, that world ocean is infinite source of heavy water, of deuterium. So, and then if you would go to nowadays, the global warming, ecological society, you know, new greener thinking says, no, we need fusion not in that long time. We need fusion before tipping point for global warming. And I overheard the previous, the former Secretary of Energy, Stephen Chu, even remarked, if fusion is only in 50 years from now, we don't need such fusion because of the tipping point. So this is what actually happened. So coming back to the intermediate source of energy as nuclear fission reactors, which initially people thought could serve us for 200, maybe more, up to 2,000 years. What's happening there? It's also very interesting. Very few people follow, actually. The biggest business in conventional nuclear energy, in fission reactors, is now decommissioning. Everyone is running too close to decommission existing nuclear fission power stations because of sudden success of fracking. That's what's happening. So we have to reconsider all the fusion efforts. And in that respect, Bruno quoted several times my participation in 1985 Reagan-Gorbachev summit. Story was very interesting. Of course, the main issue which Gorbachev, our team, to bring to Geneva was how to deal with Star Wars. It would destabilize international relations. And Gorbachev said, okay, this is very important negative argument, but would you guys able to come up with something positive so we could work together with Americans? So the scientific community was invited in. We had a lot of discussions, and finally 2 proposals were suggested, and Gorbachev spelled them at the meeting with Reagan. So one proposal was for this big tokamak, which eventually was called ITER, many years after Reagan already was gone. But there was another proposal, very interesting, which was coming from Russian seismology community. They said, you know, we are worried about California. It is at tremendous risk of earthquakes. So conversation went in the following way. Gorbachev to Reagan, you know, we are worried you are endangered species, Americans. And Reagan said, and you are not? So, yes. So who was right? Now you can decide. So there was no interest on President Reagan's side to cooperate on seismology, on earthquake prediction. So our colleague Vladimir Kelly-Zborok, who was the originator of this idea of cooperation, had to take initiative, emigrated to UCLA, and he was a professor at UCLA. Probably some of you met him a number of times. He passed about a year ago. So on fusion then finally was moving. The first step in fusion was 8 billion size proposal, ITER-1. And there was a lot of criticism, and there was a collective open letter in Science about 10 years ago. Bruno and myself, we were co-signatories. We were arguing against ITER-1 because the physics was not yet clarified, and it was too expensive. It was very expensive. The requirement were to have $8 billion. So there were other critics, and the US Congress finally declined to continue ITER-1 project. So a couple of years later, ITER-2 came, said, oh, okay, we are saving money. Now it would be costing only $5 billion. So now we are talking about 55. I'm afraid that without explanation, anti-science sentiments, you know, would explode in the face of this story. Talking about fusion, I would like to to show a couple of slides. Okay, so it's what I already told it. So actually, no, interesting. The only skeptic of early fusion success was Dr. Edward Teller. He said, no, it would not come before end of 20th century. Okay, so can you imagine the time when Charlie, as a young man with a bachelor's degree from Harvard, joined Princeton Plasma Lab? Tremendous time. Everyone was expecting fusion would come very soon. Moreover, in terms of global astrophysics, it was known that at that time that 99 plus part of the universe made of a baryon matter was in state of plasma. So, and there were another applications. Charlie, in a few years, would join AFCO Everett, which was building MHD generators, which were also expected as a tremendous success. So what we should feel at that time? Very simple. We felt that we plasma physicists are masters of universe. And so when Charlie joined Princeton Plasma Lab, Lyman Spitzer was a director. And Ed Freeman was the head of theory, was the first mentor of Charlie. And I have to tell you that when Soviets in Geneva first met American fusion physicists, because until then everything was classified, the only idea in fusion which was not known, was not independently suggested on Soviet side, was a stellarator, extremely ingenious, intelligent project. And so Lyman Spitzer was a really great physicist, great thinker. Unfortunately, stellarator lost its competition at that time to tokamaks. Tokamaks very kind of straightforward, very robust, but this experiment, this projection was much more intelligent because nobody expected that you will have magnetic surfaces enveloping, providing plasma confinement without additional current, driven from external source. However, it didn't work mostly probably because there was a conflict between two irreconcilable symmetries. Helical symmetry, which provide the idea of stellarator, and toroidal symmetry when you will close it. So symmetry breakup created chaos in magnetic field lines behavior and then in the particles. So that was the future. However, nothing bad happens with a good outcome. Lyman Spitzer had to abandon eventually fusion and lab plasma, and he went back to astrophysics, and we have a lot of fruits out of this. Hubble is the first fruit. The idea of space observatory he conceived long before space age in 1946, I think. Yeah. So before Charlie had to decide what to do, there was a Sputnik launched in 57, and in 58, early 58, Van Allen radiation belts were discovered, and that became the very first extremely successful topic for Charlie to study with Harry Paychik, discovering what Herb Burke was mentioning as escape of electrons, but also protons, due to collective behavior of plasma, kind of self-organization, providing radiation belt environment more acceptable for all of us. And I can tell you an interesting story related to discovery of Van Allen radiation belts. Since Soviets were first in space with Sputnik 1, there was a very carefully prepared experiment to measure potential energetic particles in the orbit by Soviets. But Khrushchev said, no, we need first to send a dog before we will send scientific experiments. So Laika was sent in end of 57. So and then in early 58, everything was ready to launch pre-Van Allen radiation experiment by Soviets. And Korolev, who was the father of Soviet space program, summoned all the participants to find out if everything is okay before launch. Everything was okay except tape recorder to record the data along the orbit. Scientists said, no, we should not launch today. We should wait until tape recorder would be repaired. And Korolev looked at them and said, no, we are going to launch. So it was launched. Radiation, enhanced radiation, energetic protons were found only in one location, over Baikonur launching site. No more data outside. So years later, Korolev confessed what happened, why he made such an instruction. He said, very simple. I got a phone call from from Khrushchev that morning, who said he got a phone call from Italian Communist Party leader, Palmiro Togliatti. Yes. So you see, again, Italians played a role. And Togliatti said, Comrade Khrushchev, can you launch something? Tomorrow we have a parliamentary elections. If you would it would give us few more million votes. So intervention of politics is tremendous. Charlie and I, in the late 70s, co-chaired a US-Soviet working group on what to do after Apollo. Our subject was, can we have a docking between orbital station, Salyut, and shuttle, and do some more science jointly? It failed next year after Soviet invasion to Afghanistan. So, Bruno, you came up with interesting project with Velikov, Ignitor. This morning I read Russian press. Ukrainian government declared that there is a massive invasion of Russian forces into Ukraine. I doubt that now this project will go on. So Charlie was a lucky one. He left fusion almost at the beginning of his creative career, and he achieved everything. And main interest at early phases were chaotic behavior of unstable plasma leading to different leaks, like leaks of energetic particles. Second topic was collisionless shocks. And today at this session we have two talks somehow related to this issue. So I would like to ask Mischa Malkov to talk. Mischa Malkov, I remember I recruited him after he graduated from university in Moscow to Space Research Institute. He was a theorist in the group of Alex Galeev. And then in late 80s, early 90s, he spent some time, a year or two, with Charlie here in California, working together on chocolates and other stuff. And then he spent a few years in Germany, and about 10 or 15 years moved, and now he is a research scientist at La Jolla. So, okay, Mischa.
So yes, as Roald said, my name is Mischa Malkov. I am delighted to be here and to present some Charlie's early achievements and basically his legacy. He left to astrophysicists before he moved to other important activity in his career, and I'd like to thank Charlie and Ellen for inviting me here. I'm going to talk about one specific aspect of Charlie's work in plasma physics. And Bruno, by the way, complained about a lack of recognition that astrophysicists show towards plasma physics. And I'm trying to, I think I will try to convince you otherwise. So we have at least one example when astrophysicists do recognize what has been done by professionals in plasma physics. And one example is, of course, it's what Charlie did in collision shocks and energetic particles associated with them. So I will quickly, so the basic object that I'm going to talk about is cosmic rays. And I will quickly explain what it is and how collision shocks are related to cosmic rays, and then I will quickly describe some specific mechanism which is now considered to be the main mechanisms responsible for the production of these cosmic rays. Okay, and what are the cosmic rays? They are, by the way, not rays. It's a sort of misleading name. They are particles, and they've been discovered slightly more than 100 years ago by Victor Hess in this kind of brave balloon flight. And but now, of course, things changed quite a bit, and we have a full range of different instruments, of which only few are shown here. It's mostly the idea is to observe the sky at night and see what traces these cosmic rays leave in the atmosphere, and then analyzing the direction and the amount of energy ultimately released at the ground level, we can figure out what is the energy of the primary particles hitting the atmosphere. Why cosmic rays are important? If you look at the history of particle physics, you realize that in early days, up to about maybe 1950 or so, much of the progress made in particle physics was really due to cosmic rays. Most of the discoveries also awarded by a Nobel Prize, they've been made in cosmic rays. Okay. The cosmic rays, the spectrum, if you look at the energy spectrum of the cosmic rays, it's really quite amazing. It extends up to the energies of about 10 to the 20 electron volts, which is comparable to the energy of well-served tennis ball or even football. And the places where they are presumably accelerated, it depends, of course, a little bit what part of the spectrum are you looking at. Up to this point, which is called need, if you look at more carefully at the spectrum, there's a little kink here about the energy 10 to the 15 eV. These particles are most likely to be produced in these beautiful objects, which are supernova remnants. And what is actually remarkable about this object that the limbs are the collisionless shocks. That's actually what one of the Charlie's beloved subject in plasma physics, he advanced so quite significantly in 70s and 80s, and which are currently actively used in astrophysics. And so what are they? The basic concept of collisionless shocks is you can understand it if you have a flow in say, hydrodynamic flow with a relatively smooth profile of velocity, then you have particles moving faster here and slower here, and then sort of impede these slower moving particles and have to transfer their momentum and energy to them. And how to do this if there are no collisions, so the plasma is so rarefied. And the idea was that the waves should be responsible for that, and the details are quite complicated, and things have been advanced by a number of Charlie's works in this field. And then what does this all have to do with cosmic rays is that at collisionless shocks, it turns out that we can use them to accelerate particles. So if you have a profile of velocity which is suddenly changing from upstream to downstream, and particles is kind of trapped between this media and bouncing forth and back, and gains energy. And the aspect that Charlie understood quite well was the basic nonlinearity of the entire process. Not only these particles are parasitically accelerated, they also generate waves that help to confine them, and that's the subject that Charlie has advanced very substantially, and the nonlinearity is in particular reflected in the form of back reaction of these particles to the flow. Okay, then the acceleration basically consists of three major phases. One is injection, how particles get promoted from thermal continuum to some special population which can further continue bouncing forth and back, as I said, between upstream and downstream sides of the shock. And then finally, particles escape when they reach a certain energy or get into the specific part of the phase space. And all that is controlled by wave-particle interaction and self-confinement effect. When particles, they drive waves, and confinement is basically magnetic. And as Herb told us, that it's easy to confine particles across the field, but it's harder to confine them along the field. And Charlie studied ion cyclotron instability as a means to do exactly that. And so one of the seminal works was about, which helped a lot to understand injection, is this work actually analyzes the data from observations near, in front of the earthbound shock. Another very interesting and important contribution was that this deep theoretical analysis of the structure of some particular collisionless shocks. And what I think Charlie managed to do here is to demonstrate that he gave a peace of mind to the astrophysicists in the sense that collisionless shocks are not something totally mysterious. It's a real object which behave very much like regular shocks, and people started to work with them from this perspective. And really, it was a great help for the astrophysical community. Then another interesting aspect which regard actually directly the collisional shocks, and Charlie and Roald managed to build a sort of first principle model and example of quite specific collisional shocks supported by fire hose instability. And this is one of the basic plasma instabilities that Roald suggested early. And this was, I think, one of the first quite non-trivial example of collisionless shocks requiring instability and modes that support as a nonlinear entity of plasma dynamics that can support this very complicated object as collisionless shocks. And then another interesting example is also what can plasma physics can bring to the astrophysics, and what is really appreciated, and it is still having a great impact on the research in the field of cosmic ray transport, where the concept of self-confinement is now making its way to the forefront of this research. And the self-confinement is the idea that particles that are essentially unstable and in a sort of non-equilibrium state, they drive waves, and the waves help to confine these particles and keep them accelerated, etc. So there are many, of course, many other contributions that Charlie made to this field, and we are still using them, and they are appreciated. And I think Ferd Coroniti will talk more about the pulsar physics and about other aspects of high-energy astrophysics that Charlie contributed so significantly. So conclusion is simple. I want to argue against Bruno's remark that no, Charlie's work is still updated, and it's still making a very significant impact on high-energy astrophysics. Thank you.
So, I'm not contradicting what you said, but there are new information on the shock waves that came from the Voyager. I was in charge of plasma physics at the encounter with Uranus. And the shock wave in front of Uranus, it never did anything original. I learned from Roald and Charlie and so on, did not confirm what we know. For example, the oscillation in the magnetic field. You know, the shock is not like in a fluid, as you said correctly. Did not comply with the theory at all. But NASA did not like new discovery. Everything had to be according to plan. So the paper published on the shock of Uranus obeys the Iraqi-Yugoslav relation without, and that is not true. It doesn't have my name. The one on Uranus, yes, it has my name. But then there is another one brought about by the Voyager spacecraft, another crisis. They expected that the high energy particle present in the solar wind, at about 100 astronomical unit, would be generated by the so-called terminal shock. When they crossed the terminal shock, they were not generated by the terminal shock. So then there is a crisis. And one of the ideas that it would be magnetic reconnection. So I think there is need for Roald and Charlie to get that together and to consider that, because real experimental data.
Yeah, I agree that it's very hard to trace particles back to their source. That's the nature of these particles. They orbits are strongly scrambled, and
everybody was sure, that some Fermi that crossing the terminal shock that would reveal that after that there were no high energy. They come from beyond.
Sure.
Or
yeah, there are many mysterious things going on, and the same is true for supernova remnant shocks. People observe things that are not entirely consistent with our current understanding of collisional shocks, but more interesting is the future, I think. It's
Bruno, one of the great advantages in science is to be able to agree with everybody.
Yeah.
And in the case of collisionless shocks, in the formation phases of the subject, there were models of perpendicular shocks, and models of parallel shocks, and models in high beta, and models in low beta, and they all look different. And they were all right.
Yeah.
And the problem is that you have to know the parameters that in the upstream flow very precisely to know what kind of acceleration you're going to get. And so when you start studying individual crossings in space, you've got to know a lot before you know what you're talking about.
Yeah, that's exactly what is shown here from your paper.
Yeah, Bruno, with terminal shock, I think situation is that solar wind expanding is losing energy due to charge exchange with the neutral hydrogen atoms. And at the end, terminal shock has a very small Mach number, very modest Mach number.
You see, it's not
and Fermi acceleration spectra, if you use a shock model, strongly depends on the Mach number, and it is, extremely steep. It goes down very quickly with higher energy at low Mach numbers, according to this classical formula, which was derived by Roger Blanford and a few others.
But then, Roald, okay, that would explain why. But then they are made by another mechanism. What is it? Because it could be Fermi of second type.
Yes, second order Fermi. Yeah.
Well, we tried. There is a current sheet.
Yes, absolutely. And actually, I was thinking that someone would talk about reconnection work and instabilities and different detectors, which Charlie was working, especially in relation to substorms. Maybe someone would mention it.
Well, one of the key authors is coming up is Ferd.
Yeah.
And so let's give him a chance.
Yeah.
We can continue to argue. Then there'll be a coffee break and you can go at it.
Without a pointer on
So,
Ferd
Coroniti was very active, actively participating in joint works with Charlie throughout many years in UCLA. Intermittently, he was chairman of the physics department over there, and you saw his name in some of the papers on shocks. He also prominently was in reconnection field, also with Charlie, with Alex Galeev, and he was visiting. So let him speak.
Okay, thank you, Roald. I hope you'll get a pointer. So I'm going to talk about a particular astrophysical object, the Crab Nebula, that Charlie was involved with in sort of the late 1970s and early 1980s, and ended up writing two of the most famous papers in theoretical astrophysics on this object. I'll talk a little bit about what was done at that time, the basic MHD model of the Crab pulsar wind and its interaction with the nebula. And then I'll try to bring Charlie up to date, because he's had his interests elsewhere in the meantime, on what's been happening observationally in the Crab and what sort of the current status of the Crab is. If I can manage to do two things at once. Crab Nebula is a supernova remnant that was formed in an explosion in 1054 AD. It was observed in the Middle East and in China, and possibly by the Southwest Indians. If any of you have ever been to Montezuma's Castle in Arizona, there's a pictograph on the wall that we think is actually a picture of the Crab Nebula. It was visible during the day for a period of about a month or so. Gives you some idea how bright it was. Today, it's a region that's about 3 by 6 light years, or 1 by 2 parsecs in the distance units preferred by astronomers. It's still expanding with a velocity of about 1,400 kilometers a second. That's 50 times faster than the Earth goes around the sun. And the expansion rate is actually increasing, so it's accelerating. What you see in the blue light here is synchrotron radiation. It was predicted by the great Russian theoretical astrophysicist Igor Shklovsky in 1953, confirmed by measurements made in the Soviet Union and on Mount Palomar by Walter Baade in 1954. It is made by relativistic electrons and positrons that are spiraling around in magnetic fields that thread throughout this region. The red light that you see here is for hydrogen recombination radiation from the remnants of the star that exploded back then. The Crab radiates across the entire electromagnetic spectrum, the nebula itself. Here's a superposed image of the X-ray emission, the optical emission, and finally the radio emission. And notice that the highest energy photons come from the inner part of the nebula. The optical radiation extends somewhat further out, and the radio radiation fills out the whole nebula. This whole glowing region of hot relativistic particles is confined by the outermost layers of the nebula of the star that exploded. Here's the electromagnetic spectrum of the Crab. Don't expect you, this is spectral energy distribution as a function of frequency or energy up there. You can see the nebula radiates across that whole region. Main thing is that the total radiated luminosity that's coming out in photons from the nebula is 10 to the 38 ergs per second. The total energy of the nebula itself, including its expansion energy, is about 5 times that. And to put that in context, that's 100,000 times more energy than our sun puts out every second. Okay? So the Crab requires a powerful energy source that's acting today, and that energy source is, of course, the Crab pulsar. Now, the basic picture of pulsars stems from just shortly after its discovery. What a pulsar is a neutron star, an object that's about 10 kilometers in radius, but with a mass of the sun, about 1.44 times the mass of the sun, if you want to be precise about it. It's spinning on it, rotating around at, in the Crab's case, 33 milliseconds is its period, so 30 times a second, it makes one complete rotation. It's dominated by a magnetic field. It's incredibly strong. It's 4 times 10 to the 12th Gauss at the poles. That's about 1 million times stronger than we can produce on the Earth today. This magnetic field is so strong that if you send a photon through it, the photon is unstable. It breaks down into electron and positron pairs. That first model of that was worked out by Peter Goldreich and his student Julian in 1969. And they predict basically that every second, 10 to the 38th electrons and positrons are produced in these vacuum discharges that occur around the poles of the star. This plasma that's created flows out on open field lines that then makes its way from this object at 10 kilometer scale out to the Crab Nebula via a relativistic wind that carries basically the spin-down luminosity that's associated with the star. All of this is being powered by the rotational kinetic energy stored in the star, and you can calculate what that is, and that's the 5 times 10 to the 38th ergs per second to power the Crab Nebula. So all of that energy that's powering that region that's several light years in extent is coming from this little 10-kilometer object. The key parameter of this relativistic wind, which will feature in our story, is the ratio of the Poynting flux, that is the energy that's carried by the electromagnetic field, to the kinetic energy that's carried by the plasma. Michael named this sigma, and it's a notation which is stuck in the field, so I'll refer to it as the sigma issue. But it's basically just the difference between the amount of energy that the magnetic field or electromagnetic field carries and the amount of energy that's carried by the particles. The pair production models at 10 to the 38th are sufficient to explain the optical to the gamma ray emission from the nebula. That is, you need to accelerate electrons and positrons, and this is the number you need every second to explain the radiation that we see. The radio radiation requires about 3 orders of magnitude more particles per second to be produced. That remains, as you will see, a mystery. The basic structure of the nebula was worked out by Lord Morton Rees, he wasn't a lord then, but he is now, and Jim Gunn from Princeton in 1974. They simply pointed out that this relativistic wind that's coming from this little object in the center, let's see if I can steady that pointer a little bit, coming from this object in the center, the pulsar, flows out and it's supersonic. That wind, however, is confined by the remnant that was left by the supernova explosion. So there has to be a shock transition that takes you from supersonic flow to subsonic flow. And that shock transition occurs within about 1/10 of a parsec or so of the pulsar. And it occurs when the ram pressure of the wind is comparable to the thermal and magnetic pressure in the nebula. The star is spinning, and this is probably its rotation axis. The magnetic field is spun out in the equatorial plane, and the dominant relativistic wind comes out in a rotational equator of the pulsar. It wraps the magnetic field around, so the magnetic field is primarily toroidal, and what you see here is in the X-ray observations from the Chandra Observatory, basically a toroidal-like structure. And it's that toroidal-like structure that represents the magnetic field. I would say that by the late 1970s, the recent Gunn picture was pretty well confirmed. That is, we more or less understood the energetics of the nebula and more or less understood its magnetohydrodynamic structure as a consequence. And it was at this point, in the end of the 70s and early 80s, that Charlie got interested in trying to make a more refined model of this interaction as a way both of confirming the existence of a collision with shock and understanding where the plasma physics that was associated with the pulsar and with the relativistic wind could explain the observed radiation that was coming from the nebula. And so here is his calculations on an MHD flow model for the radiation from the crab. What you saw in the earlier slide is that the highest energy photons come from the nearest region around the pulsar. The lower energy photons come from further out. So the first thing Charlie did is calculate the angular width of the nebula as a function of the photon energy, ranging from about in optical photons out to several MeV energies. What you see here in the dots are the data that existed at that time, and here's the theoretical curve that Charlie calculated. The physics is simple. Synchrotron radiation, the power, it depends on the square of the energy, gamma square being related to the energy through the Lorentz factor. And so the highest energy particles emit energy more rapidly. They burn off and lose energy. And as they flow outwards from the star and into the nebula, there aren't enough high energy photons further out to make high energy radiation. So that basically explains the observed structure of the nebula as a function of frequency. The key calculation, however, in that work was the calculation of the spectrum, that is, the energy as a function of frequency that's radiated by the post-shock flow. He adopted the classic canonical cosmic ray spectrum that Mischa just talked about as the spectrum that the electrons and positrons got just behind the shock, that is in downstream flow, and worked out the radiation. These are theoretical curves. The A, B, and C were the known observational points at that time, and he basically determined a set of parameters for the relativistic wind coming from the pulsar that would explain the observed radiation and its spectral shape as well. The spectral shape is determined by the flow of the MHD flow in the nebula. The key parameter, this parameter sigma, the ratio of electromagnetic pointing flux to kinetic energy flux, he determined had to be about 0.003. Now, that confirmed a guess that Rees and Gunn had made, that the relativistic wind had to be dominated by kinetic energy. And it's a mere factor of 10 million smaller than is predicted by all current models of pulsars. Current models of pulsars say that the electromagnetic energy should dominate by many orders of magnitude than the kinetic energy that's produced in the electromagnetic breakdown of the vacuum. And even by the loose standards of theoretical astrophysics, numerology, a factor of 10 to the 7th is a bit preoccupying, as they say. Well, what I'd like to do now is say this paper was published in 1984. It still today is frequently cited. It's hard to pick up a journal of the copy of the Astrophysical Journal in which there isn't some citation to this work, even going on now. So what's happened since that time? Well, the expansion of the wind from the pulsar's magnetosphere out to the distance where it's shocked is a factor of 10 to the 9th in radius. You would expect at that point that any inhomogeneities that were associated with this pulsar and its structure and the magnetosphere would have been washed away. And so that what should be entering the nebula would be very smooth, very smoothly varying in space and temporally steady as a consequence. Here are observations from the Chandra Observatory in X-rays and from the Hubble Space Telescope in optical radiation of what the region in the immediate vicinity of the pulsar and its shock look like. And the first thing one notes is in the X-rays is hotspots. This ring here is supposed to be the shock that terminates the supersonic wind, and it should be reasonably smooth by the previous arguments, and it's not. And furthermore, it varies in these spatial bright spots vary in time. Here they're not there, here they are. The other thing is that this is still a quasi-relativistic flow. And in a relativistic flow, when the fluid is flowing at you and radiating, it boosts the frequency of the photons, and therefore the brightness of the intensity of the spectrum. When the fluid is flowing away, Doppler dims the spectrum. That simply isn't seen. There isn't any obvious dimming of the fluid that's flowing away from that that's coming toward us. In the optical, and somewhat in the X-ray still, one sees what are called wisps. These were first detected by Lansdale in 1922, followed up by pioneering work at the Lick Observatory in 1969 by Jeff Scargill. they're hotspots. And these hotspots vary in time. They also, waves tend to propagate at a sizable fraction of the speed of light from one of these wisps to the outermost ones. And this had been studied in great detail by Jim Hester using the Hubble Space Telescope. So what we've learned from the inner parts of the nebula, that what should have been a smooth shock transition is much more complicated. That the shock and the wind are spatially structured, temporally variable. Furthermore, there is no clear association with any of this nebular activity with any activity that's associated with the pulsar. And so the interaction is a little bit more complicated than we had imagined back in the early 1970s and 80s. One possibility is that the composition of the wind may be more complicated in itself. In the early 1990s, and then followed up later in 2004, John Ahrens and his students Gallant and Spitowski proposed that the wind also carries a significant flux of heavy ions that are ripped out of the surface of the star and propagate out. When these heavy ions are shocked, they basically start to gyrate in the magnetic fields downstream, and their gyro orbits are in fact macroscopic. They're on the order of a fraction of a parsec, which we can now resolve in optical telescopes anyway. And the gyrations represent currents that bunch the magnetic field, concentrate the magnetic field, and when you compress the magnetic field, that increases the synchrotron radiation. So these wisps, and this is a simulation study, of bright regions may be associated with the gyro motion that we actually see of heavy ions. The gyro orbits are unstable. As you can see, they become chaotic. They radiate magnetosonic waves, which are basically just sound waves traveling in a magnetized plasma. Those sound waves travel out from wisp 1 to wisp 2 at a significant fraction of the speed of light. So again, the situation may be more complicated than we originally figured. More recently, the Fermi Gamma Ray Observatory and the European Agio Gamma Ray Observatory detected flares that are coming from the Crab Nebula itself. These flares occur at energies in photons with energies greater than 100 million electron volts. They are not associated or correlated with any thing that's happening at the pulsar, and they are not detected at X-ray or optical wavelengths either. But a significant brightening of these very energetic gamma rays seem to indicate that rapid acceleration must be going on within the Crab Nebula itself. Here's just a picture of the energy flux from the Crab during a major flare. These flares are tapping about 1% of the spin-down luminosity of the pulsar. That's not an inconsequential amount of energy, okay? And so it's hard to understand. The best understanding of it, and to satisfy Roald, I'll mention it, has to do with a certain magical astrophysical process that goes by the name of reconnection, that the magnetic field in the nebula has regions of opposite polarity. These regions of field can come together and annihilate, converting the magnetic energy into electrical energy and particle energy. Particles then are accelerated along the neutral lines in this magnetic field. And this is recent work by Cerruti, Werner, Uzdensky, and Begelman that seem to account for the observed temporal profile of these bursts, gamma ray flares, and the spectrum. And so maybe, again, indicating that the region of the nebula itself is more complicated than we originally might have thought. And so what are today's current Crab Nebula conundrums? The sigma problem. How do you go from a Poynting-dominated flux by orders of magnitude to a kinetic energy-dominated flux, a relativistic wind? Does it occur in the zone between the pulsar and the shock? The magnetic field in here should be striped, that is, it should have regions of alternating polarity. those stripes could annihilate either in that region or at the shock itself, and give up the magnetic energy. We really don't know. The radio emission threads throughout the nebula. We still don't understand where the relativistic electrons and positrons come from that provide that radiation. Or do we understand the number of particles, or where the number of particles per second that have to carry that? The wisps downstream, are they indicating that the wind is in fact carrying a sizable flux of heavy ions? Other possibilities have been mentioned, that the nebula is MHD kink unstable and the kink are producing the wisps. And finally, the flares. They have recently discovered, is it localized reconnection or are there other instabilities going on? And so I'd like to end by just simply saying we may be facing the Kuhnian question. That's after Thomas Kuhn, the historian of science, who wrote the book The Copernican Revolution, which changed the way we viewed the progress of science. Are we simply, as in the old Aristotelian days, going to face with saving the appearances? A few tweaks of the old model, a few new bells and whistles added to it, but basically we could understand all of this. Or are we facing a more fundamental paradigm change in our understanding of the Crab nebula? The Crab has been called the Rosetta Stone of theoretical astrophysics, and it remains so today. Much of what we've understood about high energy astrophysics was first worked out for the Crab. We have in the audience today several of the world's most distinguished theoretical astrophysicists, and so perhaps they would like to comment on the Kuhnian question. But before doing so, it's always useful to remember the wise words of Willie Fowler, who in a paraphrase of a quote from Thomas Huxley, said, "The terrible tragedies of science are the horrible murders of beautiful theories by ugly facts." Thank you very much.
As a totally undistinguished observer, may I insert a couple of names in your talk?
Of course.
The Russian discovery of the polarization of the optical emission was made by a gentleman named Dombrowski.
Yeah.
It was very sad for him. He looked for optical polarization and other nebulae the rest of his career, never found anything. The American confirmation was a series of plates taken by that well-known California astronomer, Ferd.
Okay. Thank you.
Walter Bottom was also a funny fellow.
Is there any chance that dark matter could have any influence? I mean, you have a very dense region where you're getting gamma rays from space. Now, dark matter is not supposed to interact with electromagnetic theory, but could there be any other interaction?
The fluxes that we see from the Crab are just overwhelm anything at a dark matter source. Generally, on these spatial scales, dark matter should be very smooth. But when you talk about the galaxy, that's a different matter. There you begin to have enough gravity to affect the distribution of dark matter.
You know, we've been connected with the Angela group, the Discordi flares. But another phenomenon that you mentioned quickly, there is a dimple that seems to be affected by, you call it a kink instability, probably involving reconnection. We looked into it. Can you say more on that? What do you?
I don't know that much about it. And again, these observations are still relatively new.
They're new.
Yeah.
Let's hear from Martin.
This is a question, not a comment, to either of the last two speakers. We know how computer modeling has taken over much of astrophysics. And one area where this has happened is the work of Mikolsky and people like that in computing particle trajectories in relativistic shocks, etc. Would you like to comment on how far this has to go and how important it's going to be?
Mischa, perhaps that sounds like a question more to you. Yeah.
Indeed, there was a tremendous progress in simulations recently. But if you speak about particular objects like supernova remnants, for instance, where you need to simulate a particle over the entire history when it starts from the thermal pool and gets to the 10 to the 15. It's a huge dynamical range. And I think currently simulations are able to, to reproduce only piecewise this history. So they can address, for instance, the initial part of acceleration, which is called injection. Then they can reasonably well describe the middle of this story, the acceleration. But altogether, when particles start to leave, they spread over larger and larger distances, and you need bigger and bigger grid on your computer, and this is still not realistic. So,
but issues like the spectrum of the particles.
That's the thing is.
Acceleration of different species.
Yes, that's a good point. But the thing is that the nature of this acceleration process is such that the spectrum, the energy spectrum, is quite tightly coupled to the spatial scale. So if your spatial resolution in computer is limited, then the energy description is also limited in this way. You can just either describe thermal, superthermal transition well, very carefully with all the waves, or you can just have a gross picture, which, sort of.
I hate to interrupt, but I'd like to comment that one of the terrible tragedies in a conference like this is the murder of beautiful conversations by coffee break.
Right.
But I think it's time, and there's the hallways outside.
Right.
Let's thank all the speakers.
Geneva conference in 1958 with all this, the great people, like Lyman Spitzer, Marshall Rosenbluth from America coming. So I was there, and it was almost officially declared at Geneva in 1958 that fusion energy would be harnessed in 20 years. It was coming from the mouth of chairman of Geneva Conference, prominent Nobel Prize winner, Indian physicist Homi Bhabha, and Igor Tam, co-inventor of tokamak, was a co-chairman. He was sitting next to him. But you know what happened? Nobody actually noticed the rules of the game for fusion changed dramatically since that time. How initial role of fusion was very simple. So in a couple of hundred years, assumption was that we will get rid of conventional fuels, so they will move to nuclear and fission energy. And we know that how much we can extract uranium-235 out of natural uranium ores. It would probably sufficient for a few hundred years, maybe a couple of thousand years. And
this UCSD TV program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest programs.
I will start, since as a convener of this next session, and I will ask Mischa to come later. I think it's what Lou asked. It was absolutely legitimate question, and I think if society, not only bureaucracy, but society, would not be told what happened, why it was originally planned for 5 billion, ITER. Now we're talking about 55 at least. So what happened? Something, has to be clarified. So before we are going to space and astrophysics, I would like to say a few words. I'm probably the only survivor of earlier period, not 1961. I joined fusion program in Soviet Union at Kurchatov Institute since 1956. And then there was a famous nuclear energy in fission reactors is now decommissioning. Everyone is running too close to decommission existing nuclear fission power stations because of sudden success of fracking. That's what's happening. So we have to reconsider all the fusion efforts. And in that respect, Bruno quoted several times my participation in 1985 Reagan-Gorbachev summit. Story was very interesting. Of course, the main issue which Gorbachev, our team, to bring to Geneva was how to deal with Star Wars. It would destabilize international relations. And Gorbachev said, okay, this is very important negative argument, but would you guys able to come up with something positive so we could work together with Americans? So the scientific community was invited in. We had a lot of discussions, and finally 2 proposals were suggested, and Gorbachev spelled them at the meeting with Reagan. So one proposal was for this big tokamak, which eventually was called ITER, many years after Reagan already was gone. But there was another proposal, very interesting, which was coming from Russian seismology community. They said, we are worried about California. It is at tremendous risk of earthquakes. So conversation went in the following way. Gorbachev to Reagan, we are worried you are endangered species, Americans. And Reagan said, and you are not? So, yes. So who was right? Now you can decide. So there was no interest on President Reagan's side to cooperate on seismology, on earthquake prediction. So our colleague, Vladimir Kelis-Borok, who was the originator of this idea of cooperation, had to take initiative, emigrated to UCLA, and he was a professor at UCLA. Probably some of you met him a number of times. He passed about a year ago. So on fusion then finally was moving. The first step in fusion was 8 billion size proposal, ITER 1. And there was a lot of criticism. And there was a collective open letter in Science about 10 years ago. Bruno and myself, then people said, then we will use fusion. And this is how actually, Charlie, first connection between plasma physics and fusion and oceanography came, that world ocean is infinite source of heavy water, of deuterium. So, and then if you would go to nowadays, the global warming, ecological society, new greener thinking says, no, we need fusion not in that long time. We need fusion before tipping point for global warming. And I overheard the previous, the former Secretary of Energy, Stephen Chu, even remarked, if fusion is only in 50 years from now, we don't need such fusion because of the tipping point. So this is what actually happened. So coming back to the intermediate source of energy as nuclear fission reactors, which initially people thought could serve us for 200, maybe more, up to 2,000 years. What's happening there? It's also very interesting. Very few people follow, actually. The biggest business in conventional